Hello, this is the exam review slides for Exam 1 and Organic Chemistry 2 for Fall 2021 semester. So this exam is going to be on SN1, SN2, E1 and E2 reactions, as well as the reactions that it add to alkenes. Okay, so you're going to have one mechanism from either one of these four types. Okay, so we're going to go through the E1 and the SN1 because those are typically the more difficult. Okay? And so one of the things you can do is you can come in and draw in the hydrogens. Okay, so CH3, 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 C. All right. Here we have CH3, CH. 3C, CH2. Okay, so we're gonna be grabbing a hold of one of these hydrogens, right? It's an E1 mechanism. I'm gonna tell you which one I want to see. But for an SN1 and E1, right, the mechanism is exactly the same. The leaving group leaves, and you're left with this. So CH3. Remember, we're going to have to grab one of those hydrogens. Okay, so there's a carbocation there, the bromine left, so it takes those electrons with it for a new lone pair. And then the base comes in, grabs this hydrogen, these electrons collapse this way, and you end up with that product. I said, okay, well, I want to see an SN1, right? Again, you can come in here and so you could draw in the hydrogens. All right, so CH3, CH2, C, CH3, CH2, CH3. And none of the hydrogens seem to be moving, so that's a good sign. Okay, but again, for an SN1 type mechanism, right, the leaving group leaves, and you're left with this. Fine, plus Br minus. And here, it's the carbon that comes in to make a bond, right? Because we're making this new carbon-carbon bond, so it needs to be these two lone pair comes in here to make the new bond, and so there it is. So you're just going to have one of these type of mechanisms, or it could also be an SN2 or an E2, something like that, but you're going to have one of those. But I can get you to study all of them. The other one would be a methyl or a hydride shift. Okay, and so this one can only be an SN1 or an E1 mechanism. Okay, so the first thing you're going to want to do for this one is draw in the hydrogens. So CH3, right, there's an H here, there's an H here, CH3, CH2, CH2, CH3. Right, over here it's CH3, CH2, C, CH3, CH, CH2, CH3. And if you notice, the only ones that change are these right here. Okay. So it goes from a CH to a CH2. The middle carbon here goes from a CH to no hydrogens on it, and this one also goes from a CH2 to a CH. Okay, so that's those three that are going to change. Okay. And so, right, first thing that happens, right, for an E1, right, leaving group leaves. And so you end up with that. Carbocation here, your bromide leaving group. Now, for this one, right, we need to get a hydrogen over here. Okay, we need to go from a CH to a CH2, and having that charge on there is a good opportunity to move things around. And so what we're going to want to do is we're going to want to move this hydrogen here over there. And so if we do that, right, we end up with this hydrogen here. Right, so now we've solved two problems, right? So this carbon goes from a CH to a CH2, right, where we need it to. We've removed the one hydrogen that we needed to from here, right, going to CH to C, right? We just need to be able to remove that hydrogen, and that's where the base comes into play. And so the base will come in, grab that hydrogen, collapse down. You could have the bromide come in and grab it. That's not a big deal. And so that gives the final product here. But the important thing is to see the hydride move over, and you can figure that out by looking at what the what the hydrogens look like in the starting material and then the product, and you can see what changes. And that'll give you a hint as to what needs to move around. So you do need to know with stereochemistry for SN1 and SN2. So remember for an SN2 reaction, if it's an R, it's going to go to an S. S goes to R, right? Because your backside attack, you end up getting that inversion. But for SN1, it doesn't matter which you start with, right? The carbocation intermediate is going to remove any information that you had before, and so you're going to get an equal mixture of R and S. You're going to get both. So if we did this reaction here, right? Here's the here's the nucleophile. Right? So if this is the nucleophile, you have to look for that polar covalent bond. That's right here. And so this is going to get attracted. It's going to want to make a bond here, but again, it has to go from the back side. And since the bromine is coming out at you because it's on a wedge, that means the OH has to come behind. Oops. Try that again. And so when that happens, we're going to get plus Br minus. And your nucleophile is going to be on a wedge. So if your leaving group is on a wedge, I'm sorry, it's on a dash. Leaving group's on a wedge, you're going to end up with a dash. So for an E1 mechanism, right, you have to figure out, in this case, we're going to have a base. So we have to find the base, so that's here. So now we need to find the leaving group over here, and that's right here. So this is the leaving group. And so we need to look at, are there CH bonds attached to this, to the carbon with the leaving group? Okay. Well, there's one here, CH2. Right, there's one here. Right, and there's one here. So what we're going to get is if we make it between the blue carbon and the red, right, remember that leaves and the base is going to come in and grab that hydrogen, so you're going to end up with this product here. If you go from the blue carbon to the green carbon, if we remove this hydrogen, that's going to collapse down and form this product. And if you go between the blue carbon and the purple one, right, we're going to make a carbon-carbon bond between there. Like that. Now, it turns out that these are the same molecule. Right, the red and blue are just flipped. If you just take this molecule and flip it over, right? But it's a nice little exercise, right? Because this is where the leaving group was, and so we're looking at all the carbons around it. Okay, so those are the same. So we're going to have these two, and so these guys are going to be the major product, right? Because what you're going to want to do is you're going to look to see, okay, how many hydrogens are directly on, these carbon-carbon bonds, right? And so for this one, there's 3 bonds shown, so there's 1 H, right? 1 H. There's none here, right? Because all 4 bonds are shown. For here, there's no hydrogens, right? Because all 4 bonds are shown. But here it's a CH2, right? Because there's only 2 bonds shown. So Zaitsev says, hey, you want the more substituted more substituted alkene that's formed. That means you have fewer hydrogens on it, and so this is going to be the major product. So for here, right, you have an SN1, right, and so remember, so you have to look for the base, right, or look for the nucleophile. That's actually going to be here, and you say like, well, hold on, why isn't it the bromine? Well, bromines are a really, really poorly nucleophile, right, because it's a very it has a very low pKa, so HBr is a really terrible, or HBr is a really strong acid, so it's a terrible base. OH minus, right, it's like water. Water isn't particularly acidic, and so that makes it a good nucleophile. So what we're looking for is, and then we're looking for the polar covalent bond, and that's on the other one, and so that's here. So this is going to end up attacking there. Now, the thing is, it's an SN1, and so it's the leaving group leaving, and then this coming in. And so, but remember with SN1, it doesn't matter what you end up getting. You get an S and an R. Okay, so you're going to get a mixture of both. So you're going to get this. The H ends up leaving as HPR. Bromine comes back and snatches it. But then you're also going to make this product. Going to make like that. For here, right? Here's our base. So for an E2 reaction, base. So now we're looking for a leaving group. So this is our leaving group. Okay. So for this carbon here, we're looking on either side, right? So we look on the red carbon. Oops. Right? There's an H there. So we can make a bond between this red carbon here and the blue. So if we do that, you're going to end up with this. If we go between the blue and this orange here, this one has 3 hydrogens on it. So it has at least 1, so that's fine. So plus, so we're going to make that, and then plus Cl minus and CH3OH. Technical. Okay, so if we're looking at hydrogens directly on the carbons of the alkene, so there's only 1 hydrogen over here, none here, so there's 1 hydrogen. Here there's 1 hydrogen, and this is 2 hydrogens, so this has 3 hydrogens on it. So the red one's the more substituted of these two, and so this is going to be the major product. Now, for the alkene reactions, okay, the important part of this chart is actually over here. Okay, what you're going to say is alkene, right? Because that's what we've been talking about for the previous chapter, and then I've talked about. Okay, so we have alkene. So alkene plus so alkene plus HX, where HX is a halide, right? So as the HX across the alkene, but the X goes on the carbon end, that's more substitute, the higher number of this, right? So the H would go here, and the X would go over here. XX, you're going to do the same thing, adds across that. So what you need to do is, so this is actually just to illustrate what's going on in here, but by knowing this stuff, you're going to be able to apply it to no matter what the molecule looks like. You're just going to say alkene plus, the mercury compound. That's oxymercuration. That means I'm adding HOH across the double bond, but in this case, the OH goes on the higher ordered side. So this is there to illustrate it. Okay, so this is how you would want to do these, study these reactions. Same thing with this. Now we are going to have a predict the reagent, right? So you can say, okay, we've got alkene. We're going to be, right, so here's where the alkene used to be. We're going to add BR to it. So HBr isn't really going to do anything, right, because we need to add Br on both sides. So what does that do? Well, that we're going to need reagent D. So for here, right, here's our alkene, right, is right here, but we're going to add HOH across it, right, because it's an H. But are we adding to the higher or lower side? Well, here this is tertiary, this is secondary. We're adding it to the lower ordered side, the OH to the lower order. That means the anti-Markovnikov. And so that means we're going to need to do hydroboration. So that's how you do this. Now for predict the product, right? If you've got this, I'm going to draw this a little bit larger. So you got this, alkene, ozone. This should be plus HCl or something like that. Okay, what does this do? Well, it takes, right, picks an alkene and it slices it. And so it'll literally, you could literally draw it like this. Like that. So here's your product. Now for this one down below, right? Alkene, osmium. So here's the reagent. So how does this change? So for this one, the osmium, it ends up adding OHs across both sides. So that means our product is going to be this. That. For this one here, right? So with that, here's the alkene. And what is this? Oh, here's the mercury here, right? So what does that do? Well, that puts an HOH across it. Okay, but the OH is going to go on the higher ordered side. And if you notice, I'm saying it the exact same way that it's written on the list of reactions. Right? How you have to think about this. So, right, this is secondary. Right? That's primary. Right? This is going to follow Markovnikov. So we're going to put the OH on the higher ordered side. So your product is going to look like this. OH like this, and you're going to have an extra H over there. You can put the H in, you don't have to. This H, you put the OH there. Now for MCPBA, right? Right? We have alkene. So for the MCPBA, what does that do? That so in here it forms the epoxide. So that's going to form it right here. So you're going to end up with this product. That. This is where the original alkene was. Right here and right here. I'm going to put that bridging oxygen. Now for this one here, here's the alkene. And we do have chlorine. Okay. but there's also water involved. And so what that's going to do is that's going to put a Cl on one side and an OH on the other. That's the halohydrin. If the water wasn't around, you would just add Cl's to both sides. But for here, the OH is going to go on the higher ordered side because it ends up getting added second. And so if you look here versus here, right, the one on these two carbons, right? So this is tertiary, right? While the other one's primary. And so what we're going to end up with is this. So the OH going on the higher ordered side and the Cl on the lower. That's it. Good luck.